Hello, everyone. Welcome back to the part 4 of digital and computer system architecture. We talk about the thread and data load parallelism. Okay, as we mentioned in last lecture, right? So we figured out the instruction level parallelism really cannot go very far because instructions are like that. They have dependencies, right? So that's why we have to involve some human efforts. That's why we say, okay, we need to involve human efforts like thread level parallelism and data level parallelism. Thread level parallelism requires the programmers to explicitly represent how each thread can execute on what in parallel. The goal is to use multiple instruction streams to improve the throughput of computer that can run many programs and the execution time of multi-threaded programs. And thread level parallelism could be much more cost-effective than instruction level parallelism. Or on the other hand, when you ask the programmer to tell you something, right, it's definitely better than they didn't tell you anything. The new approach like multi-threaded execution. Multi-threaded execution means multiple threads to share the function units of one processor by overlapping the processor must duplicate independent states of each thread, a separate copy of the register file, a separate PC, and for running independent programs, a separate page table. Memory is shared through the virtual memory mechanisms, which always support multi-processes. There's hardware for faster thread switching, much faster than full process switch. It's typically 100 to 1,000 clock cycles. It's 100 and 1,000 times faster than like a full process switch. When switching, there are different ways, like alternating instruction per iteration, per thread, like fine-grained, or we only switch when there is a long stall, like cache miss. Fine-grained multi-threading switches between threads on every instruction, causing the execution of multiple threads to be interleaved. This is usually done in round-robin fashion, skipping any start threads. CPU must be able to switch threads every clock. The advantage is it can hide both short and long stalls, since the instructions from other threads execute when one thread stalls. Right? The disadvantage is it slows down the execution of individual threads, since a thread ready to execute without stall will be delayed by instructions from other threads because it's fine-grained. Coarse-grained multi-threading, switching threads only when costly stalls happen, such as L2 cache miss. The advantage is there's no need for very fast thread switching, right? Because we're typically only do switching when the coarse-grained, like a long stall happens. So fast switching, which costs a lot of hardware, is not really much needed. Not slow down the threads, since the instructions from one thread can continue execute until you encounter a very costly stall. So those stalls are like overlapped by other instructions that's executing on the CPU. Well, the disadvantage is it is hard to overcome the throughput losses from shorter stalls due to pipeline starting up cost, because we don't have fast thread switching anymore. Then we have short stalls. It's quite expensive for you to do switching. Since CPU issues instructions from one thread, when a stall occurs, the pipeline must be emptied or frozen. New threads must fill pipeline before instruction can complete. Right? Because of this startup overhead, coarse-grained multi-threading is better for reducing penalty when you have a very long stall, right? So these are the illustrations of simultaneous multi-threading. Simultaneous multi-threading means we allow multiple threads to execute simultaneously. Like at one clock cycle, we can have two memory access and one fx is fixed point, floating point, branch, and condition codes to be executed at the same cycle. So Instead of allowing one thread to execute at a time, we allow multiple threads to execute simultaneously. This is going to multi-core, right? Simultaneous multi-threading, the insight is that we have for many hardware mechanisms support like multi-threading. So if we do multi-threading, why don't we use multiple hardware, right? So allow different threads to execute simultaneously. A large set of virtual registers that can be used to hold register sets of independent threads are required. We need a register renaming provide unique register identifiers, so instructions from multiple threads can be mixed in data paths without confusing sources and destinations across different threads. So basically, the registers also have to know which thread it comes from. Out of order completion allows the thread to execute out of order and get better utilization of the hardware. Just adding a per thread renaming table and keeping separate pieces will be adequate, right? We allow different threads to have their own private PC and a register renaming table. Multi-threading categories like superscala, executing one instruction at one thread at a time. Fine grain, like every cycle, we have only one instruction, right? One thread to execute. Coarse grain is only to switching for quite a while. Multi-processing means you have multiple processes to work on different cores. Simultaneous multi-threading means we can, at the same time, different threads can execute on different cores, right? So for those of you who don't know what is a process, and what is a thread, we're going to give a very brief introduction. So for process, it means there's no context sharing between different processes. So they are totally isolated, like page table, definite context, and a lot of other things. Well, for threads, they can actually share the page table, okay? Even they have different PCs and register renaming tables, but they can share the page table. They also can share, it's possible but not required, right? They can share also the virtual address to physical address translation. They can also share the virtual address. Basically, they're on the same process. It's like one process can have multiple threads. Okay. But another process cannot share anything with this process, except some very security intense known sharing, like through virtual to hardware sharing and other communication pipes. So basically, the process is much heavier than a thread. That's what we're trying to say here. So once we have thread level parallelism, like what we showed here, we're going to definitely give you very detailed discussion about thread level parallelism in 2 lectures later. But right now, let's give an invasion here. So once we have like a thread level parallelism, can we also include the instruction level parallelism? The answer is yes, we can do that. So basically, what we do is for different threads, they can still do pipelining, those kind of things. Put a process-oriented at instruction level parallelism to exploit TLP. Function units are often idle in data paths designed for instruction level parallelism because of either stores or dependencies in the code. So typically, you cannot do that if you have the instruction level parallelism oriented process. But in thread level parallelism oriented process, they can use instruction level parallelism. Could the thread level parallelism be used as a source of independent instructions that might keep the processor busy during stalls? Yes. Could TLP be used to exploit the function units that would otherwise lie idle when insufficient ILP exists? Yes. Design challenges in, okay, so to answer these two questions, right, first, could the TLP be used as a source of independent instructions that might keep the processor busy during stalls? So I think this is something we have to keep in mind that thread level parallelism only works per thread, and instead of a thread, you're doing instruction level parallelism, right? So if in one instruction you have some stalls, the thread level parallelism cannot kick in. Could TLP be used to employ the function units that would otherwise lie idle when insufficient instruction level parallelism exists? This is also not possible if we take instruction level parallelism as an orientation. Okay, so because we have to first talk about thread level parallelism, and then we talk about instruction level parallelism. So basically, if you have the instruction level parallelism, some stalls, the thread level parallelism cannot take advantage of that. Design challenges in simultaneous multi-threading. Since simultaneous multi-threading makes sense only when fine-grained implementation happens, right? So we need to address the challenges faced by fine-grained scheduling, such as the switching, right? The preferred thread approach sacrifices neither throughput nor single-threaded performance. Larger register files are needed to hold multiple contexts, not affecting clock cycle time, especially in instruction issue. What kind of instructions needs to be considered? Instruction completion, choosing which instruction to commit might be challenging. Ensuring that the cache and TLB conflicts generated by SMT do not degrade the performance, right? So when you have multiple threads comes in, how you deal with this kind of busy waiting problem? This is what we're mentioning here, right? So a preferred threads approach would definitely sacrifice some throughputs or some performances. So that's why SMT should treat all threads the same. Okay. So right now we have a couple of different ideas, like a speculative dynamic schedule deeply pipelined SMT, speculative dynamic scheduled superscala, speculative dynamic scheduled SMT, 2 CPU cores per chip, statically scheduled ones. We see these are the configurations: fetch, issue, and execute are 334, 334, 848, 6511 function units. This one's the most, right? Clock rates. This one is the highest because it's a single core. And then total transistor size. So this is space constraint. 125 million, 140, 114 million, 200 million, 592 million, and the power. So this one also consumes the most because it has the most transistors and spaces consumption. But as you can see here, for some cases, Italian is the best, right? For some cases, Pentium is the best. For some cases, AMD is the best. AMD is the best. AMD is the best. Let's see. AMD. AMD, and then Itanium. Okay. AMD. Then we have Pentium. It's the best. Pentium best. Pentium best. Pentium best. PowerPC, which uses multi-core, actually performs the worst because of the clock rates and number of function units are lowest. Well, even it has more transistors, right? But this also tells us when it goes to floating point operation, PowerPC becomes better, right? So PowerPC, let's use a diamond here. Okay. Okay, so I just added the benchmark names of the stack FP 2000, as you can see here. So PowerPC has pretty good performance for quite a bit of the applications, and then Itanium is this. Good. And then we have AMD is what? Triangle, sorry. So Itanium is triangle. See here. Can't use that. MD is square. So as you can see here, in this case, it seems like what? AMD is the best, right? In this case, PowerPC is the best. So what's the, and here about the efficiency, right? Normalized performance. As you can see, for different cases like transistors, high is better. Stack ink per stack FP per transistor, say AMD is better. And then space complexity, AMD is the better. Well, for power consumption, PowerPC is better, right? So they have different efficiencies. So the obvious takeaway is that there's no obvious overall leader in the performance of like both integer and floating point, and also efficiency, right? So these things we already discussed just now, right? So can we use 15 minutes to discuss what are the differences and connections between multi-core processor versus multi-threading? Okay. And then we're going to do midterm review.